What specific problem does the proposed method Lynx address in the field of hallucination detection in language models?
The proposed method Lynx addresses the specific problem of hallucination detection in language models, particularly focusing on intrinsic hallucinations. In the context of retrieval-augmented generation RAG systems, hallucinations occur when the generated answers by the language models are not faithful to the context provided. Lynx aims to provide a reference-free metric for automated RAG evaluation by detecting whether the generated answers are consistent with the context. This is crucial for ensuring the outputs of large language models are grounded in factual information and do not contain inaccuracies or false information. Lynx outperforms existing models like GPT-4o and closed-source LLMs in hallucination detection tasks, especially in specialized domains such as finance and medicine. By training on data from multiple domains and focusing on hard-to-detect hallucinations, Lynx offers a high-quality, open-source solution for evaluating the faithfulness of language model outputs in RAG settings.
How does the proposed method Lynx work in detecting hallucinations step by step?
The proposed method Lynx works in detecting hallucinations step by step as follows. 1. Construction of hallucination examples. Lynx sources examples from existing QA datasets and introduces perturbations to generate hallucinated answers that appear plausible but are not faithful to the context. The perturbed examples are challenging for LLM judges due to nuanced differences in semantic meaning that can lead to different reasoning outcomes. 2. HaluBench construction. Lynx constructs HaluBench, a large-scale hallucination evaluation benchmark consisting of 15K samples across multiple real-world domains such as finance and medicine. The benchmark includes tasks sourced from various QA datasets and synthetic data perturbations to create a comprehensive evaluation benchmark. 3. Human annotation. To verify the quality of the data and the effectiveness of the perturbation process, a subset of examples from different datasets is manually checked by expert annotators. The human agreement on the quality of the data is high, indicating the reliability of the constructed examples. 4. Model training. Lynx is trained using a training dataset consisting of 2,400 samples sourced from various datasets like RAG-Truth, Drop COVID QA, and PubMed QA. The training dataset includes both faithful and hallucinated answers for model learning. 5. Self-instruct tuning. Lynx is fine-tuned using the Llama 3 to 70B instruct and Llama 3 to 8B instruct checkpoints on the training dataset. The model is trained to output reasoning and a final score, pass or fail, based on the evaluation task provided in the instruction. 6. Evaluation results. Lynx is evaluated on HaluBench to assess its performance in hallucination detection. The model is prompted to assess the faithfulness of responses to the context and provide reasoning for the score. Lynx outperforms other closed and open-source models, reporting the highest accuracy on all evaluation tasks, especially in domain-specific tasks like medical answers in PubMed QA. In summary, Lynx detects hallucinations by constructing perturbed examples, creating a comprehensive evaluation benchmark, training the model on diverse datasets, fine-tuning using self-instruct tuning, and evaluating its performance on real-world tasks to achieve high accuracy in detecting hallucinations.
What are the theoretical or practical benefits of using Lynx for hallucination detection compared to existing alternatives?
The theoretical and practical benefits of using Lynx for hallucination detection compared to existing alternatives are significant. The paper highlights that Lynx 70B outperforms both GPT-4o and closed-source LLMs in hallucination detection tasks, demonstrating higher accuracy on all evaluation tasks. Lynx 70B shows an average increase in accuracy of almost 1% compared to GPT-4o across all tasks, with an even more pronounced difference in domain-specific tasks like medical answers in PubMed QA, where Lynx 70B is 8.3% more accurate. Additionally, Lynx 8B and Lynx 70B exhibit improved accuracy compared to the baseline Llama 3 models, with the fine-tuned 70B model resulting in a 7. 8% increase in average accuracy. When compared to closed-source LLMs, Lynx outperforms GPT-3.5 Turbo by a significant margin, with an average increase of 27.6% across all tasks. Lynx 70B emerges as the best-performing model overall, achieving an accuracy of 87.4% on HaluBench, showcasing its superiority in hallucination detection tasks. These results demonstrate that Lynx provides a more effective and accurate solution for hallucination detection in real-world settings compared to existing alternatives, offering improved performance, especially in specialized domains like finance and medicine.
How is the method Lynx validated or tested in the paper?
The method Lynx is validated and tested in the paper through the construction of a hallucination evaluation benchmark called HaluBench. This benchmark consists of 15K samples of context question-answer triplets annotated for the presence of hallucinations. The samples are sourced from real-world domains such as finance and medicine, making the benchmark diverse and comprehensive. Lynx is trained on this benchmark, along with data from existing QA datasets like COVID QA, Drop Finance Bench, and PubMed QA. The model is fine-tuned using the Llama 3 to 70B instruct checkpoint, and is trained to output reasoning chains and evaluation scores similar to natural language inference tasks. Human annotators manually check a subset of examples from the benchmark to ensure the quality of the data and the effectiveness of the perturbation generator in inducing hallucinations. Lynx is then evaluated on HaluBench to assess its performance in detecting hallucinations in real-world settings. The results show that Lynx outperforms both open-source and closed-source models, including GPT-4o and GPT-3.5 Turbo, demonstrating its effectiveness in hallucination detection tasks across various domains.
What results were achieved with the proposed method, Lynx, in terms of performance on HaluBench and other evaluation tasks?
Lynx achieved the highest accuracy on all evaluation tasks on HaluBench compared to other closed and open-source models. Specifically, Lynx 70B outperformed GPT-4o by almost 1% accuracy on average across all tasks. In domain-specific tasks, Lynx 70B showed an even more significant difference, being 8.3% more accurate than GPT-4o in identifying inaccurate responses in medical answers from PubMed QA. Both Lynx 8B and Lynx 70B demonstrated increased accuracy on all tasks compared to the baseline Llama 3 models, with the fine-tuned 70B model resulting in a 7.8% increase in average accuracy. When compared to closed-source LLMs, Lynx outperformed GPT-3.5 Turbo by a wider margin, with an average increase of 27.6% across all tasks. Overall, Lynx 70B emerged as the best-performing model with an accuracy of 87.4% on HaluBench, while GPT-3.5 Turbo exhibited the lowest accuracy among all models evaluated, averaging 58.7% accuracy across all tasks.
What are the limitations or drawbacks of using Lynx for hallucination detection in language models?
The limitations or drawbacks of using Lynx for hallucination detection in language models include the reliance on semantic perturbations to generate unfaithful answers, which may not capture the full spectrum of hallucinations that can occur in real-world scenarios. Additionally, Lynx focuses solely on intrinsic hallucination evaluation, neglecting extrinsic hallucinations that do not align with factual reality. The model's training data is sourced from a limited number of datasets, which may not fully represent the diverse range of contexts and questions encountered in practical applications. Lynx's performance may vary depending on the quality and diversity of the training data, potentially leading to biases or inaccuracies in hallucination detection. Furthermore, the reliance on human annotation for verifying the quality of generated samples may introduce subjectivity and variability in the evaluation process. Lastly, Lynx's effectiveness in detecting hallucinations may be limited by the complexity and nuances of language, as it requires models to perform nuanced reasoning and disambiguation, which can be challenging for current language models.